I'd first like to thank all the organizers for letting me speak today. And this is joint work with Peter Nelson. Okay, the goal of this talk is to answer the following question. How many elements can a simple GFP representable matroid with no rank T+2 projective geometry minor have? And, well, okay, so we will answer this question by finding the growth rate function for this class, growth rate function or extremal function. And I'll first show a construction that gives a lower bound on the growth rate function. And then I'll show how we can use the matroid minor structure theorem to find an upper bound. Okay, so this is the same function that Owen and Kevin talked about. I will just call it the growth rate function instead of the extremal function. And just a couple examples to make sure we're on the same page. The growth rate function for the class of graphic matroids is n+1 choose 2 because a simple graph on at most n+1 vertices has at most n+1 choose 2 edges. And equality is attained by cliques. And the growth rate function for the class of GFP representable matroids is p to the n-1 over p-1 because a GFP matrix with at most n rows has at most that many non-zero columns such that no two are parallel. And of course, equality is attained by projective geometries. Okay, so we will let m sub pt denote the class of GFP representable matroids with no PG T+1 P minor. And now our concrete goal is to determine the growth rate function for this class for each odd prime P and each non-negative integer T. And the results of this talk hold for binary matroids as well, but the construction is different, so I won't discuss that. Okay, so we'll first find a lower bound, and we will use gamma frame matroids. We'll let gamma, these were first introduced by Zaslavsky. We will let gamma be a subgroup of the multiplicative group of GFP. And a gamma frame matrix is a GFP matrix such that each column has at most 2 non-zero entries. Each column with a non-zero entry contains a 1. And each column with 2 non-zero entries contains a 1 and negative alpha for some alpha in our subgroup gamma. And then a gamma frame matroid is a matroid with a representation as a gamma frame matrix. And for this talk, you don't need to worry about this definition too much. We just need 2 properties of gamma frame matroids. The first is that the class of gamma frame matroids is minor closed for any gamma. And that's easy to check. The second property we need is that the class of gamma frame matroids has growth rate function, the size of gamma times n choose 2 plus n. And that's just because if we have a gamma frame matrix with at most n rows, there's certainly at most n unit columns. And if we have a column with 2 non-zero entries, there's n choose 2 choices for the rows for those entries. And since we want the columns to, we want to make sure that no 2 columns are parallel, we'll say that the top entry is 1, and then there's a size of gamma choices for the other entry. Okay, so now we can use gamma frame matroids to find a lower bound on our growth rate function. So we'll let gamma be a subgroup of the multiplicative group of GFP of size p-1 over 2. So it's the largest possible proper subgroup. And we will consider the class of matroids which have a representation as a gamma frame matrix with up to t additional rows. And it turns out that matroids in this class have no PG T+1 P minor. So why is that true? Well, this class is minor closed. And that follows quickly from the fact that the class of gamma frame matroids is minor closed. So then we just have to check to see whether a rank T plus 2 matroid in this class can be a projective geometry. And you can just use a simple counting argument to show that that can't be true. So a simple rank T plus 2 matroid in this class just can't have enough elements to be a projective geometry. So now we have this class of matroids with no PG T plus 1 P minor. So for each positive integer n, we just want to take a matroid in this class with lots of elements, as many elements as possible. And I think the natural way to do that is to take a gamma frame matrix with n minus t rows, and for each non-zero column, we just want to pair it with every possible length t vector. So that gives us the following function, which I'll denote f sub pt. So, okay, so in the parentheses here, this is the maximum possible number of columns that a gamma frame matrix with n minus t rows can have, such that no two are parallel. And then we have this p to the t here, because we are pairing each such column with every possible length t vector. And then there's also, we can have p to the t minus 1 over p minus 1 columns for which the gamma frame matrix has a 0 column. So that's where this function comes from. And again, since matroids in this class have no PG T plus 1 P minor, this gives us a lower bound on the growth rate function for m sub pt. And just note that this function is quadratic in n because of the n minus t choose 2. And the leading coefficient is about roughly p to the t. So it's a nice function. So we have a lower bound. What can we say about an upper bound on the growth rate function? So just immediately by the growth rate theorem, since we're working over a prime field and we have a proper subclass of matroids, we have a quadratic upper bound. So there's some constant c such that c times n squared is an upper bound on our growth rate function. So that means that our lower bound is asymptotically correct. It's quadratic. But it turns out that our lower bound is also an upper bound for sufficiently large ranks. And there's 3 main steps to the proof. The first step is to show that there are extremal matroids in m sub pt which are highly vertically connected. And by extremal, I just mean the matroids in the class which have the maximum possible number of elements for their rank. And step 1 just follows from the growth rate theorem and a theorem of Gielen and Nelson on quadratically dense minor closed classes of matroids. And the reason we need step 1 is so that we can apply the matroid minor structure theorem. Kevin just talked about this, and it basically says that the highly vertically connected matroids in our class are highly structured. They conform to templates. And then the last step is to show that these highly structured, highly vertically connected simple matroids in our class, the number of elements is upper bounded by f. And I'll stop there. Thank you.